NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Hey, good evening, ladies and gentlemen. How's everyone tonight? Good. Well, again, thank you for coming out to join us tonight. Cassini's findings have revolutionized our understanding of Saturn, its complex rings, the amazing assortment of moons, and the planet's dynamic magnetic environment. The robotic spacecraft arrived in 2004 after a 7-year flight from Earth, dropped a parachuted probe to study the atmosphere and surface of Saturn's big moon Titan, and commenced making astonishing discoveries that continue today. Icy jets shoot from the tiny moon Enceladus, and on Titan, hydrocarbon lakes and seas are dominated by liquid ethane and methane, and complex prebiotic chemicals form in the atmosphere, then rain to the surface. Cassini's findings at Saturn have also fundamentally altered many of our concepts of how planets form around stars. Tonight's talk will present highlights from 10 years of Cassini's ambitious inquiry at Saturn. Tonight's guest received her BA from Cal State Fullerton, her MS from Cal State Los Angeles, and her PhD from UCLA, and is now a NASA research scientist here at JPL, where she has worked for 37 years. Currently, she is the Cassini project scientist and a co-investigator on the Cassini Composite Infrared Spectrometer team. She has worked on Cassini since 1988, but has also worked on the Voyager project and conducted independent research on the origin and evolution of planetary ring systems, and has received 2 NASA Exceptional Service Medals, one for long-term Cassini service, the other for her outstanding work and leadership on the Voyager-Neptune encounter. She is also very active in outreach, regularly engaging in all manner of public and academic outreach activities. She graduated from Valencia High School in Placentia and was selected as the 1998-99 Hall of Fame recipient for the Placentia Yorba Linda Unified School District, and she's also received Distinguished Alumni Awards from both Cal State LA and Cal State Fullerton. Ladies and gentlemen, please help me welcome our guest tonight, Dr. Linda Spilker.
Well, thank you very much, Mark. I'm very happy to be here tonight. In fact, just 2 weeks ago, Cassini celebrated its 10-year anniversary. That's 10 years in orbit around Saturn. Yeah, big milestone. And if you go back that 10 years, the Cassini spacecraft had to successfully execute a 96-minute nail-biting burn. Had we missed that rocket engine firing or had it gone short by as much as 5 minutes, we would have continued on our way out of the Saturn system. Instead, we completed the burn and we became the first man-made object to be in orbit around Saturn. And Cassini also carried the Huygens probe, and I'll be telling you more about that tonight. So I'll be covering the highlights of the 10 years and give you a preview of the 3 years that we have left in the mission. Here you see the Cassini spacecraft on your left. It's about 22 feet tall, about the size of a small school bus. That white antenna at the top is about 13 feet in diameter, and you can see people in the view for scale. And NASA provided the Cassini spacecraft. And on your right is the European-built Huygens probe that parachuted down to the surface of Saturn's large moon Titan. Now, the pair of them together weighed about 2.8 tons. And when you added all the fuel for Cassini, you had 6 tons of mass that you had to launch and get to Saturn. So over half of Cassini actually consisted of rocket fuel. Where did Cassini and Huygens get their names? Well, the Cassini spacecraft is named after Giovanni Domenici Cassini. He was the one that discovered the Cassini division. It's the gap right there in Saturn's rings between the A and the B rings. And he also discovered a number of moons in the Saturn system. Now, in case of the Huygens probe, it's named after a Dutch astronomer, Christian Huygens, and he discovered Titan. So it was very appropriate to name the Huygens mission after the discoverer of that moon. And he also determined that what the rings really were. They weren't solid sheets of material rotating around Saturn, but rather individual particles circling Saturn. So he contributed in that way as well. Here's the Cassini spacecraft. You can see the high-gain antenna at the top of the image. We use that high-gain antenna to collect science. We can make measurements of the atmospheres of Saturn and Titan, and also of the rings using the radio signal and how much it's absorbed as it goes through these media. We also use the high-gain antenna for radar, and we can use the radar to map the surface of Titan through a haze that's very thick and hard to see through. We have a long magnetometer boom to measure the magnetic fields around Saturn and look for magnetic fields around any of its moons. There's a cosmic dust analyzer that can measure the composition of the icy particles in the Saturn system. There's a remote sensing palette. On that palette, there are cameras, spectrometers. We measure everything from ultraviolet out into the far infrared, making actually temperature measurements in the far infrared, so a long spread of wavelength coverage. Fields and particles palette, there we measure electrons, protons, ions, neutrals at a variety of energies, making in situ measurements of basically the plasma that's in the Saturn system, and actually sniffing out bits and pieces of things like the plume on Enceladus. You can just see the side of the Huygens probe. Cassini is powered by 3 radioisotope thermoelectric generators. Basically, we take the heat from the decay of plutonium, turn that heat into electricity, and power the spacecraft. And we had about 700 watts at the start of the mission. And then you can see the 2 main engines. We had 2 because we had to have such a long burn to get into orbit around Saturn. Now, 17 countries contributed to Cassini. In particular, the Italian Space Agency contributed the communication system, and each of these countries, whose flags are represented here, contributed hardware. Scientists were truly an international team, international family at this point of scientists from a variety of countries in Europe and the United States as well. And we've actually been working together since 1990 when the instruments were selected, and you get to know people pretty well after all that time. Here's the Cassini launch, launched October 15th, 1997 from the Kennedy Space Center. It was a pre-dawn launch, and my husband Tom and I, we took our daughters to the launch, and they were thinking, oh great, we get to get out of a week of school, this is going to be really cool, it's going to be really great. But then we gave them the bad news. This launch is really early in the morning, and you're going to have to get up early, and in fact it took several times because there were launch delays, etc., before finally success. And I remember watching that launch as Cassini went up into a cloud, and the cloud lit up, and the first thing I thought, what if the spacecraft had exploded, the rocket had exploded? But then sure enough, a little bit later, the spacecraft came out from the cloud, and it was clear that all was well. We were so far away that you could see that rocket lift up from the launch pad, and it took many seconds, many tens of seconds, to actually hear and feel the roar of that rocket as Cassini started on its journey. Now, if you look at the diagram here, you can see we didn't take the direct route from the Earth to Saturn. We had a large spacecraft, and so we took advantage of gravity assists, 2 of Venus, 1 of the Earth, a gravity assist of Jupiter, and then on out to Saturn for a 7-year cruise period. And you can think of it, we slowed each of those planets down just a little tiny bit, and we speeded up Cassini an awful lot. So we basically borrowed some energy, just like having a huge additional rocket booster, and that got us on our way to Saturn. And here's an artist's concept of our arrival at Saturn. The spacecraft is actually coming out of the screen toward you, and we've turned the rocket engines to slow us down so that we can go into orbit around Saturn. And what an exciting evening that was. And I want to share with you just a clip from that time from Saturn orbit insertion.
Good evening and welcome to Cassini-Huygens Mission Control at NASA's Jet Propulsion Laboratory in Pasadena, California. The flight team is in place for SOI, that is Saturn Orbit Insertion, and that is when the spacecraft must be captured by Saturn's gravity or it will fly right on past the planet and the mission is over.
Time to turn back around to the SOI burn attitude or pointing position and light up the rockets.
We have a Doppler signature with engine turn on.
Do that.
It's 9:05 p.m. Pacific Daylight Time. The SOI burn is approximately 92% complete, and we expect to track Doppler now through the end of the burn.
Flight is going up.
Go ahead and look, huh?
The the Doppler has flattened out.
Okay, we have burn complete here.
4 years for this moment.
What a wonderful evening that was. I have fond memories of being there with my family and nieces and nephews, my mom, all of us there watching as Cassini went into orbit. And what an exciting time that was. Well, here's a little bit about the Cassini mission itself. The mission phases are shown. Turns out it takes Saturn 30 years to go around the sun a single time. And from 2004 until the end of the mission in 2017, we'll have been at Saturn almost 2 complete seasons. We arrived just after northern winter solstice and will be there through northern summer solstice. Our prime mission from 2004 to 2008 was 4 years long. That was followed by a 2-year equinox mission where we watched as the sun was edged onto the rings, a very unique and exciting time. If you're a ring scientist like I am, that was a very neat part of the mission. And now we're in our 7-year solstice mission from 2010 through 2017. And that will culminate, as I said, with the Saturn summer solstice. And Cassini, right now, is about here. You know, we're halfway through 2014, so we have a little over 3 years to go in that mission. And we're ending the mission because by that point in time, I mean, that fuel gauge, that needle is getting close to empty. And we figure that by 2017, that will be the time to end the mission. We have a very exciting set of orbits. We're going to pull in very close to the rings and then actually hop over them and orbit in a gap in between the top of the planet's atmosphere and the rings. And I'll talk a little bit more about that as I go along. But basically, a unique opportunity to explore a place that we haven't been before, and it really is a new mission to do that. Now, when we look at the science on Cassini, the Saturn system is very diverse. There are a lot of targets to look at. One of those are the rings. Shown here. The rings are composed of billions of icy particles that range in size from tiny marbles to mountain-sized particles, and so we have a lot to study about the rings themselves. Then there's the magnetosphere. You can see tiny Saturn in the center there, and there's this huge magnetic bubble created by Saturn's magnetic field that holds off the solar wind that pushes against it. And so we study all of the interactions inside that magnetic bubble. Then there's Saturn itself. We were fortunate enough to be there to witness a storm that only occurs once every 30 years, and you'll hear a little bit more about that in my talk tonight. The icy moons, there are 62 of them, but several dozen of them are outside captured objects, and there's just a few dozen that are in very close to Saturn that we can fly by and get very close to. And then, of course, giant Titan. Titan is a huge world. Had it formed elsewhere in the solar system, it could have been a planet in its own right. This is our first look at Saturn coming in, and one of the first things we noticed here is it's southern summer, and you can see just a hint of blue in the northern hemisphere. And we got a close look. The ring shadow was covering up the northern hemisphere and had a bluish, almost Neptune color to it. Very, very beautiful and unexpected, because when the Voyagers had flown by, it was close to equinox, and so the planet looked like its typical golden color that you'd see in a telescope from the Earth. Just a short time ago, we see now that those colors, those greens and blues in the north, are slowly fading, and we're starting to see those begin to appear in the south. Seasons are changing on Saturn, and we're there to be able to watch it. And that moon there in the picture is giant Titan. Here's one of my favorite views of Saturn. It's a view taken in October by Cassini, and we're high up above the North Pole looking down on Saturn. And I really love this image because the rings look like a giant bullseye around the planet. You can see them all the way around, which is really cool. And you can see Saturn's shadow going out to the side. Now, Saturn is made mostly of hydrogen and helium, very light elements. It's a giant planet. If you could build a bathtub big enough, Saturn would actually float. So how big is Saturn? Well, here's the Earth on the left to scale, and the moon on the right, and the distance between them to scale as well. It would take 764 Earths to fit inside Saturn to fill it up. So Saturn truly is a giant planet, one of the gas giant planets in our solar system. And you could see it would be an interesting sight to have Saturn in between the Earth and the moon. Let's look a little bit more closely at this North Polar region, there's a very interesting feature there. It's actually a hexagonal, a six-sided jet stream. Voyager first saw it back in the early 1980s, and it's still there today. Why it has six sides, how it can keep going that way, we don't really know. No other planets, not the Earth, Jupiter, Saturn, even the south pole of Saturn, doesn't have a hexagon. So it's truly a unique feature in the solar system. And here in this color view, you can see that it's greenish in color. The haze particles are smaller right now inside the hexagon. And as the sun keeps shining for summer inside of it, slowly we think that'll turn a more golden color. And I have a movie of the hexagon. This is in false color. It's a 10-hour movie. You can actually see the clouds shifting around, and the jet stream zips around at something like 220 miles per hour. So it's really a very, very fast jet stream centered right on Saturn's North Pole. This was kind of fun. It turns out that Bob Berman identified the 50 weirdest objects in the cosmos. And he said that the weirdest things in the universe are automatically the most fascinating. And in particular, he pulled out the top 5, and he said the final top 5 are particularly mind-blowing. So we've been talking about the hexagon. No surprise that at number 3, there is Saturn's hexagon. And so it's very interesting. So he thought about that, and his opinion was perhaps the hexagon is proof of extraterrestrial intelligence. Now that's how you could get a hexagon that would last so long at Saturn. So that was really a lot of fun to see that. Well, inside the hexagon and at its very center is a giant hurricane. The hexagon is about 2 Earths across. Inside of that is a giant hurricane right at the North Pole of the planet. In fact, this giant hurricane would span half the continental United States, from Washington, D.C. to Tulsa, Oklahoma. So it's an huge hurricane. It's been there. We're not sure exactly how long, but we think it'll last a long time. There's no solid surface underneath or any way for it to really dissipate. The sun's coming in from the right, and you can actually see the shadows from the eye wall in the center of the hurricane. And I have a little movie of the hurricane as well. This dot that you see, that's the sun in this long movie, and you can actually see the different clouds not only rotating, but changing shape as you go around this orbit inside this giant hurricane. Just a little bit about a giant storm. In December of 2010, Cassini noticed a small white cloud in the northern hemisphere. We hadn't seen any storms yet really in the northern hemisphere. And the ground-based observers were right there with us watching as this storm evolved. It started out as looked like a giant thundercloud. Up above, we had the atmosphere streaming by, creating a tail that wrapped around until finally the tail wrapped completely around. And these storms only occur about once every 30 years, once a Saturn year, typically in the spring, summer time frame. And this is only the 6th such storm that we've seen on Saturn. So it's really remarkable to be there to witness it. This is what the storm looked like in the visible. If you look in the near infrared, you can see deeper in the atmosphere. Now that greenish spot that you see there, that's actually the head of the storm, the vortex that's forming the storm. If you look at even longer wavelengths, in the upper atmosphere, there was a huge beacon looking like a giant eye sort of staring out at you. The atmosphere got very, very hot. Saturn released a tremendous amount of energy. Some people even said Saturn gave a giant burp as it released all of this heat up into the atmosphere. Here's a false color view sort of tracking over a period of months how the storm evolved. In the top view, that with the yellow on the edge there, that's the head of the storm. In this view, red is the lowest in the atmosphere, green is intermediate, and blue are the highest levels of the cloud. So you can see here's the head of the storm. It spun off a vortex, that counterclockwise rotating vortice, and as time went on, this was moving more slowly than the head of the storm. So here's the vortex again, here's the head of the storm. Bit by bit, they came closer and closer together until in June, they were just a little bit apart. And then the next time we made this map, the head and this vortex had come together, and that marked the end of the storm. It was over except for a very turbulent zone and this little vortex that survived the encounter with the head of the storm. And we're still seeing effects in that band in Saturn's atmosphere in the north. Here's another view. This is in the near infrared, and the colors are different wavelengths. The blue is reflected light. You can see the reflected light coming from the rings. If you look at longer wavelengths, green is 3 to 4 microns. And here's the aurora at the south pole of Saturn. And the aurora here are a greenish color. That's telling us something in particular about the particle size. And also we have information on composition. And then you can actually see heat coming from the planet here as well in the reds and blues. As you look to longer wavelengths, you're no longer seeing visible light. You're actually seeing heat coming out from inside of Saturn. Another very interesting finding was that Saturn has something called Saturn kilometric radiation. It's a radio beam that rotates around about once every 10.5 hours. It's kind of like a lighthouse beam, and it sweeps across Cassini. You can see it sweeping across as it beams out there and making very strong signals. And when Voyager flew by, we thought, oh, we've got the rotation rate for the interior of the planet, something very fundamental in trying to understand Saturn. The problem was that 20 years later, here comes Cassini, and the period's different by 6 minutes. And we know Saturn couldn't have slowed down. It's just too big to have slowed down by 6 minutes. So that told us that Saturn kilometric radiation is coming from elsewhere, maybe the auroral region. We're still puzzling about what's creating it and how it might work. Here's a plot that shows that the time is a function of the period that you're looking at, and Cassini found not one period, but two. Each hemisphere has a slightly different period, and we're not sure why that would be so. 2 different periods in the north, it's about 10.6 hours. In the south here, it's about 10.9. They crossed slightly after equinox. Then the storm occurred, and that sort of threw everything off kilter. We were expecting a nice symmetric pattern to come out, but it's very chaotic still, probably the result of the storm. So we're hoping by the end of the mission to have a good feeling for where does this Saturn kilometric radiation actually come from. Well, let's move on and look at the rings. The rings have names that are very easy to remember for Saturn's main rings. It's just A, B, C, D, E, F, G, and that we have so far for the rings, main rings themselves. Here's the Cassini division and the Encke gap. The F ring is just outside the main rings. Here's the G ring in between the F ring, and here's the E ring, greatest at Enceladus. But the E ring actually goes all the way into Mimas and all the way out to Titan. Those tiny little particles get moved around by the sun and by the magnetospheric interactions with the planet. Here's an even better view of the rings. The B ring has the most material, and it's the brightest of all of the rings. Here's the A ring and the C ring. They both have kind of a grayish color. We're puzzled. Does that mean that these rings formed at different times, formed of different material? We're just not sure what that answer might be. Or maybe the less thick rings get polluted, and it shows the pollution a little faster. The micrometeoroids come in, hit the rings, and bring in non-icy material. The rings are mostly water ice, except for this very small little piece of non-icy contaminant. We're not sure exactly what it is. Ring particles, as I said, from marbles to mountain sized, and there's a very interesting another idea about what the rings might be made of. Have you ever wondered what happens to your luggage when it doesn't show up at LAX? Maybe it goes all the way out to Saturn. And this is a t-shirt that I found, and I thought it was a great t-shirt. So maybe the rings are really lost airline luggage. So now you know if it doesn't show up. Here's a view of Saturn's rings that you won't see from the Earth. This is looking at the unlit side, or the side that the sun isn't shining on. And here the thick rings like the B ring are very dark. The thinner regions actually let some sunlight through, and so just a very, very unique view. What I want to show you next is a little movie. If you could ride along with the Cassini spacecraft as it goes diving from the lit side to the unlit side of the rings. Here you see the very bright B ring, Cassini division, and A ring. Every once in a while you'll see a little moon wander by. And you'll see that this thickest ring, there goes Titan. That thickest ring, the B ring, actually blocks most of the sunlight. And so here it is very dark on the other side. Now the dusty ringlets in the Cassini division are very prominent, and the A ring is sort of in between, so it lets some sunlight through, and you can see it, and you can just see a hint of the C ring. It too, like the Cassini division, lets a lot of sunlight through. So and then now you saw just at the very tail end the F ring as well. Here's the view that we had of Saturn and the rings at equinox. At equinox, it's like turning the sun off with regard to the rings, because it's just edge on with respect to the rings. In this particular mosaic, it's made up of 75 pictures, and in this case, the rings would be very dark. They'd be so dark that you wouldn't be able to see them. So what we did is we brightened up the rings on the lit side by about a factor of 20, so that you could even see them. And they're brightened up by about a factor of 60 on the unlit side, because the only light illuminating the rings at equinox is coming from the planet itself. So light from Saturn is actually shining down now on both sides of the rings, and that's the ring illumination. And what's so cool about this time is any three-dimensional structures that stick up above or below the rings, which are only about 30 feet thick on average, will stick up, catch the sunlight, and cast shadows. So here was our chance to take the rings from just a flat sheet of material and see what might be contained inside them. And sure enough, we did see places with long shadows. This is the Keeler gap. This is the outer edge of the A-ring. You can see the tiny moon Daphnis with its long shadow. And we noticed that along the edge of the gap that's created by Daphnis pushing the ring particles out of the way, that there were these structures also casting shadows. It told us that Daphnis's orbit was tipped just a little bit with respect to the rings, and so it's literally pulling material vertically from the edges of the ring, creating these huge long shadows, in some cases several miles long. Another very interesting place, this is the outer edge of the B ring. There are these particles in the B ring. We didn't know they were there. They're 1 to 2 miles in size, casting very long shadows. Here's the outer edge of the B ring. And there are just tens of these objects, large objects, bigger than we would expect for typical ring particles. Imagine a crowded freeway where the cars get so close together that sometimes they stick. And we think that's what happens to these ring particles, and they grow larger and larger and larger particles. And one good analogy for looking at these shadows is imagine you're on the space shuttle, you're looking down at Egypt, and you want to find the pyramids. And if you look down at noon, it's going to be really hard because they're sort of the same color as the background desert, and they don't have any long shadows. But if you come back and look again near dusk, you'll see these very long shadows from the pyramids, just like the long shadows from these objects, and you'll be able to pick them out. So in the same way, we had a chance to pick out these objects. What's really interesting is that the way these objects stick together tell us about how our solar system may have formed. Because there was material in the solar system initially in the same way that stuck together into planetesimals and formed our solar system, and formed solar systems around other stars. So you have the rings like a giant laboratory helping us understand how planets form around other stars. The rings are also very good at detecting meteors that hit them and letting us know. This is again in the equinox time period. The ring's surface area is about 100 times the surface area of the Earth. So they get lots and lots of impacts. An impact, you can see the streak right here. What we think happens is a meteor comes through, it gets broken apart into all of these different pieces. The pieces come around one orbit later, hit the rings again, and create a cloud of debris. Originally, the cloud is going to be a circular shape like this, but Saturn's rotation, it goes at different speeds as you go around the planet, shears it out so that little cloud gets turned into a streak. And so we could see these little streaks all over in the rings. In fact, we can make estimates of how big the objects were. In this case, this object that went into the A-ring was about the size of the Chelyabinsk meteor that impacted in Russia. So there's a lot of action happening in the rings as well. We also noticed that perhaps there was a new feature. This is the discovery image of the feature. There was a little feature on the outer edge of the A-ring. If you blow it up a little bit, we think that there's actually an object that's perturbing that outer edge, and we might be seeing the birth of a new moon. It could be that as those ring particles grow larger and larger, maybe eventually they spawn a tiny new moon. And this one was a lot of fun. The moon's nickname was Peggy. Turns out that Carl Murray discovered it, and it was his mother-in-law's birthday. So he decided to nickname this new object after his mother-in-law. And it's amazing. To this day, people keep asking me, has Peggy left the rings yet? You know, where's Peggy today? You know, so it's really made a very interesting story. And here, going back and looking at our equinox data, here are little proto-Peggy clumps. You know, Peggy's about 2 miles across, and these clumps here are maybe only half a mile across. So these clumps may grow large enough and then can actually go on and create a moon. In fact, there's one idea that maybe Saturn's rings were 10 times more massive than what we see today, and maybe they actually spawned some of the moons in the Saturn system by clumping up material and sort of letting them go bit by bit, and maybe some of these pieces came together, creating Saturn's moons. So that's another way you can actually go ahead and get moons. So let's move on to looking at some of the satellites, some of the moons in the Saturn system. Here they are. Titan is clearly the largest of the moons, and this shows some of the sizes of the other ones. In fact, just for scale, here are the inner planets, Mercury through Mars. And if you looked at the size of Titan, it's about the size of the planet Mercury. So if Titan had formed elsewhere, it could have been a planet. It just happened to form around Saturn, which is a whole lot bigger. And so it orbits Saturn instead. And Titan has a thick atmosphere, thick, dense atmosphere, mostly nitrogen. It's 4 times denser than the atmosphere in this room. It contains methane as well. That methane goes up to the top, and it's broken apart by sunlight and forms long-chained hydrocarbons, Los Angeles smog, and so you don't get to see through to the surface of Titan very often. So it's a very interesting moon. Some of the smaller moons, here's just sort of a family portrait of some of the smaller moons. Some of them, like tiny Methone, have no craters whatsoever. Others have more rugged cratered terrain. I really like Prometheus. Prometheus orbits near the F ring, and it has its central piece, but it has a skirt, probably of ring particles that it's accreted and is carrying around with it. So all kinds of interesting shapes and sizes. You don't necessarily get a spherical moon when you're that tiny. Just going to show you a little bit about some of the other moons in the Saturn system. One of the first moons we flew by was Phoebe. We actually flew by Phoebe before Saturn orbit insertion. And Phoebe, we think, is a captured Kuiper Belt object. So here was a chance to study objects that formed further away in the solar system. So on the left is the inbound view of Phoebe, and on the right is the outbound view. You can see it's very rugged and dark and has lots of craters. There's hints of water ice, though, as it looks like material has slid down. Turns out that Phoebe also gets bombarded by particles and radiation, and there's a ring associated with Phoebe, a huge ring, and some of that Phoebe ring material goes into the inner Saturn system, and it actually coats one of Saturn's other moons. This is Iapetus. Iapetus is about 900 miles across. Here's the leading side. It's all coated with Phoebe dust. Here's the trailing side. You can see a little bit of the Phoebe dust even creeping around the sides. If we look at Iapetus a little more closely, this is on the dark side now, you can see there are places where objects have poked through that layer of dust in some of the craters. And what we notice is that there is this large ridge, you can see in the bottom picture. It's a several mile high ridge, about 15 mile high ridge that goes completely around. And in fact, Iapetus looks like a giant walnut. Why it formed that way and how it got the giant ridge that seems to go all the way around, that's an interesting puzzle. Maybe it's from how Iapetus cooled off. That ridge is very old because it's covered with craters. So the ridge formed, and then there was a period of heavy cratering that occurred, and you can see those craters sort of eating away all along that particular ridge. Another very interesting world is Hyperion, about 165 miles from top to bottom. It's irregularly shaped. You can see all different kinds of craters, and Phoebe dust inside some of the craters on Hyperion as well. And if we look more closely at some of those, you can see that dark material is in the crater floors. And in the same way that if you've ever had snow on a sunny day, that the snow melts first where you have patches of earth, in the same way that dark material seems to be melting into Phoebe, or into Hyperion, excuse me. And not only do these moons return really excellent scientific data, they're also space art. So starting in 2005, this particular image got selected by Time magazine and a number of others as sort of the image of the year for space art. And ever since 2005, you can always find someone who has picked out one or more of our images and really like them. In fact, if you can go online and you'll notice that there are not only posters, but you can find pendants and jewelry and earrings, all with Cassini pictures on them. So you can find all kinds of interesting things. Let's talk a little bit about Titan. This is what Titan looks like in the visible, and this is the Titan that the Voyagers saw. We couldn't see through to the surface, and we just really wanted to know what did the surface of Titan look like. So when we went back with Cassini, we made sure to carry instruments that could see through to the surface, and in particular, carried a radar instrument, and also carried the Huygens probe. And the job of the Huygens probe was to get down through the haze and land on the surface and take pictures and measurements on the way down. So here's a little movie about Cassini. On December 24th, in 2004, we released the Huygens probe. Then we did a maneuver so we didn't follow the probe into the atmosphere of Titan. We didn't want to follow it along. The probe encountered the atmosphere, heated up, burned away its gold-colored blankets. You could see the material melting away and ablating as the probe hit the atmosphere, and actually had to slow down quite a bit to actually release the parachute. After we'd slowed down enough, a parachute came out, and that allowed the heat shield to be dropped away. There's actually, I think, a piece here that loops a little bit there. It just shows, again, the same kind of thing with pulling away the Huygens spacecraft. You can see the heat shield will drop away here in a second. And there the probe is free. And it's now taking in Saturn, atmosphere from Titan and making measurements about its composition. And you'll see here it's actually sending the data back to the Cassini spacecraft. Didn't send it all the way back to Earth, but as we were flying by with Cassini, the Huygens probe, there it goes, is squirting data, pictures, information about composition back to the spacecraft. We went to a smaller parachute because we only had a certain battery life, and the atmosphere of Titan is so dense we wanted to make sure to get down to the surface. Here you can see Titan. See the Huygens probe was actually turning a little bit and taking images as it went along. So there we landed on the surface. And then here are just a series of those, a snapshot of the images. You can see the distance as we're getting closer and closer to the surface, the number of images. At first, we don't really see any detail. And then all of a sudden, you get below about 25 kilometers. All of a sudden, there's all of this interesting detail. You start to see what look like river channels, what look like shorelines, what look like perhaps dry lake beds as you're getting closer and closer, until finally you get down to the surface with the probe and have all these pictures to sort through. But this is what it would look like if you were looking out of one of the ports of the cameras. And there's the picture from the surface. So we unveiled with the Huygens probe, this is putting some of the pictures together. We saw a chain of hills or mountains. We also saw river channels, and sure enough, what looked like a shoreline and turned out to be a dry lake bed. Turns out that methane plays the role on Titan that water plays on Earth. It can be a liquid, it can be a gas and form cloud, so it can rain methane. Methane can fill rivers, lakes, and it can actually be an ice as well. So you have a very hauntingly familiar world at minus about 212 Fahrenheit, so it's very cold. The water ice is frozen, but methane plays the role of water on Titan. And then here finally are the icy pebbles that we saw when we actually landed on the surface of Titan. So that was very exciting. We continued to send back data actually for quite some time, and the probe was hotter than the surface, so you saw these gases coming out that you could actually measure. Here are some of those gases. Not only do you have methane, CH4, you have nitrogen, you have other hydrocarbons, argon, carbon dioxide. So really a prebiotic world, what the Earth may have been like before life started on the Earth. And now here's a view of Titan in the near infrared. And we'll see if we can get this globe to rotate. The brown areas are actually dunes. These hazy particles form and rain down and actually form the equivalent of hydrocarbon dunes on the surface of Titan. And as we said, we saw mountains and dunes and river channels and lots of very interesting topography on Titan. Here's another view in the near infrared, and we could just see hints of these dark features here. Turns out that Titan has huge seas as well as lakes. Most of them are at the North Pole. There's one little one at the South Pole. And we found this very intriguing liquid lakes of liquid methane. And we didn't know for sure if they were liquid at first. We could see that they were very smooth in the radar data. But what really verified that they were liquid is when we saw this. It's a specular reflection. If the sun is just at the right angle, hits a liquid surface and bounces back at the same angle, and Cassini's in the right place to see the specular reflection, you can say now with certainty the lakes are filled with liquid. You know, we didn't know if it was like a gummy, tarry substance or what, but indeed the lakes are filled with liquid. And here's just one of the many radar shots that we got of one of those seas. This is Ligeia Mare. It's the second largest sea on Titan. It's about 50% larger than Lake Superior. You can see all of the river channels coming in and filling it. You can actually see islands inside of Ligeia Mare. And just recently, we figured out a very clever way to actually probe all the way down to the bottom of the lake. And they're about 500 feet deep, which is about the depth of the Great Lakes. So it's just an interesting coincidence that the Great Sea here would be the same depth as the Great Lakes. And what's really intriguing to me to think about is, Titan has a liquid ocean underneath its icy crust, but it also has these methane lakes. And it's a possibility that maybe you could have a very unusual form of life that could exist in liquid methane instead of liquid water. So it would be a totally different kind of biology than what we have here on the Earth. But astrobiologists are very intrigued and would really like to go back and land something in one of those lakes and try and see, could there possibly be life that could exist in the lakes? Well, Titan has seasonal change as well. We've been watching recently at the South Pole the formation of a south polar cloud. Here's a little movie of it as it rotates around. We think that this cloud will just continue, this hood will grow bigger and bigger as winter continues to approach at the South Pole. Well, the final moon I want to talk about is Enceladus. Enceladus is only 300 miles across. It's 1/10 the size of Titan. And yet it's very unusual. It's unusual because it's so bright. We knew from Voyager it was bright. In places there are very few craters, including the South Pole. There are essentially no craters at the South Pole. The craters tell us about the age of the moon, and so it's telling us that parts of the surface are very young compared to other moons that are heavily cratered. When the Voyagers flew by Enceladus in the 1980s, the South Pole was in darkness. So we missed something very significant with Voyager. Those bluish, what we nicknamed tiger stripe fractures. They're tectonic fractures, cracks in the ice, if you will. And so they're very unusual features in a region with no craters. Our first clue that something unusual is going on with Enceladus came from the magnetometer data. In this view here, you see Saturn, you see the magnetic field lines flowing out of Saturn in the purple. And if you have a solid body with no atmosphere, the magnetic field line should go to the surface. In the case of Enceladus, the magnetometer team said, hey, they're not going to the surface. It's like Enceladus has an atmosphere of some sort, and the atmosphere is maybe thickest at the South Pole. Enceladus looks more like a comet than it looks like a moon. And so with that, we decided we have to go closer. We want to see what's going on with tiny Enceladus. So we went closer, and one of the things that we got is we had a chance to see that the South Pole was very hot, much hotter than we would have expected it to be. And in looking in greater detail, where you see the yellow and the red here, the hottest parts of Enceladus were along the tiger stripes at the South Pole. So bit by bit, we were putting pieces of the puzzle together until finally we saw that Enceladus had geysers coming out, basically water vapor, water ice particles coming out from those tiger stripe fractures. And here's just a little movie showing those jets. Here's an even higher resolution. There are over 100 of them coming out of those tiger stripes. And those jets vary a little bit by about a factor of 3, depending on where you are in the orbit, that the stresses tend to pull apart and close the tiger stripes with time. And so we actually see variation in the amount of emission. And we also see salts, we see carbon dioxide, we see ammonia, we see basic ingredients that tell us you have liquid water, you have heat, and you have the ingredients to have a habitat for life. Not only that, Enceladus is sending us free samples. The trouble is Cassini doesn't have any instruments on board to be able to detect any biomarkers for life. We never thought it would be possible when we first went there with Cassini. So if we ever go back to Enceladus, and I hope we do, we need to go back with an instrument to, we fly through the plume with Cassini, but we just don't have the instruments to fly through the plume, or even better yet, collect samples, bring the samples back to Earth, and look in detail to see if there might be some kind of life inside this tiny moon. So very unexpected. Well, between the Huygens probe landing on Titan and these are probably the two most fundamental discoveries that were made by Cassini. And here's just another view. You can see some of the individual jets, even you can see them in this forward scatter view, the sun shining through the particles. If you've ever had a dusty windshield and you drive into the sun on an afternoon, you know how hard it is to see through that dust. And so the dust just lights up as the sun shines through it. So you can see all of the jets on the surface of Enceladus. Just want to show you a couple more pictures. These are just close-ups now of some of those fractures. We actually saw evidence of what looked like tiny little boulders that maybe got coughed up by some of these geysers that went back on the surface. Most of the material falls back on the surface, and that's why there are no craters. that are there on Enceladus. So you can just see how tectonically active, how torn apart that south polar surface is. Here's another one. You almost get the sense of material, sort of a haze coming up out of one of those tiger stripes. So we have a few very, very high resolution shots. What we think is happening is that there's a liquid water reservoir underneath, and that comes up through a crack, and that this is the icy geyser that comes out with ice grains and gas coming out that creates these jets. And just recently, in fact, just this year, we had enough gravity flybys to put together to say definitively there is a liquid ocean underneath the South Pole. It's about 6 miles thick, and it's under an icy crust that's 10 to 20 miles thick. So you have to get from this liquid ocean up to these water jets coming out. So you know that there's a very extensive ocean, and that ocean is in contact with a rocky core, which is providing the materials that could also support life. So it'd sure be interesting to go back and see what's there. The few particles that do escape go on to form Enceladus's E-ring. Here's tiny Enceladus. You can see the jets here, and the very tiniest particles that don't fall back go on to form this very, very tenuous E-ring. And as soon as Enceladus plumes shut off, then those particles are so tiny that the solar pressure and the magnetic field will take the E-ring away. So if we ever look back someday from the Earth and the E-ring's gone, that's telling us that the plumes would have shut off in the intervening years. This is a view again with the sun shining through those icy particles. And one of my very favorite pictures is this one. This is a mosaic that we put together. We took this image, this set of images, about a year ago. And you can see the sunlight shining through this very beautiful blue E-ring. Here's Saturn's G-ring and the main rings themselves. If we blow it up a little bit, you'll notice there's a white ring that goes all around Saturn. And what's happening is the sunlight is being refracted through Saturn's atmosphere to Cassini cameras. And if you think about it, you're seeing every sunrise and sunset on Saturn at the same time. Just kind of a really cool thing to be able to see. And you also see that there's light on the dark side of Saturn. And in this case, the sunlight is reflected from the rings onto the dark side of Saturn. You can actually see the shadows of the rings as they cut across the planet as well. So very beautiful, but scientifically interesting as well. And not only did we have Saturn in the picture, but we had 3 other planets. Turns out that we had got pictures of Mars and Venus and the Earth and the Moon. And we spent 20 minutes taking pictures of the Earth and the Moon so we could get a color snapshot of our world, of that pale blue dot. And you can clearly distinguish, Earth is there on the left, the Moon on the right. And as part of this event, it was on July 19th, just a year ago, we asked people to go outside. We told them where in the sky to find Saturn, to go outside, smile, and wave at Saturn, and let your photons become part of this historic image from 900 million miles away. So how many people here waved at Saturn on July 19th? Yay, there's people. Yeah, Tom and I went out and we waved. We were in Kansas. We went out and waved at Saturn. We asked people also as they were waving, send us pictures of yourself waving. We want to capture those selfies. This is a historic moment. Sort of the whole world comes together to go out and wave at a point in the sky that's this little tiny planet, Saturn. So we collected those pictures. We had pictures of people holding up their dog's paw waving. We had families waving. We had clubs waving in classes. And just people, the excitement and enthusiasm was really wonderful to see. So when you have this many selfies, you got a few thousand selfies, what are you going to do with them? Well, you're going to recreate the Saturn mosaic. And if you look carefully, those are all pictures. And if you were one of those waving and sent us your picture, you can go onto our website and you can look through, and it's like a giant jigsaw puzzle. You can find yourself in those particular images. So that was really a lot of fun. Tremendous, tremendous enthusiasm and support. Sort of the day the Earth smiled and waved at Saturn. What more could you ask for? It was really great. Well, recently we also had a contest. We asked people, help us name this very exciting end of mission phase. As you're diving between the rings and the top of the atmosphere, we had called it the proximal orbits, meaning proximal, meaning close to Saturn. We thought, I bet the public can do better than that. They can help us come up with a really cool name. And so they did. And the winner, we got over 2,000 entries. The winner was the Cassini Grand Finale. And so when we go through these set of orbits, when the fuel is running low, what we're going to do is we're going to be so close to Saturn, we're going to study its gravity field and magnetic field and learn something about the interior structure of this world. And that's going to help us understand how our solar system formed and how other solar systems might form. We're going to measure the mass of the rings. Now, I think that's really cool. The mass of the rings is uncertain by 100%. That's a large error bar. and if the rings are more massive, maybe they formed at the same time as Saturn and they're old. If they're not as massive, then we know that perhaps a comet or two came too close to Saturn and Saturn's gravity just ripped it to shreds, or a moon wandered too close. So we'll be able to tell something about the origin of Saturn's rings as well. So that's very exciting. Also, as we sample in that region, we're going where no one has gone before, and we're going to sample ring particles directly, measure their composition, sample the atmosphere directly, upper atmosphere of Saturn, measure its composition, look for radiation belts in there, and do all kinds of exciting things in this very new regime. So now if you could ride along with the Cassini spacecraft through one of these end-of-mission orbits, here's what you might see. You're coming in at 70,000 miles per hour, you're going very fast, and in just a few seconds you're crossing through that plane of material that we hope is not much material there. We'll be pointing the high-gain antenna down as a shield for the first few orbits, and it's going to be 7 seconds of terror every 7 days for 22 orbits. Just imagine, that we're going to really, especially that first one, going through that very first time. And it might be like standing on the bridge of the Enterprise and looking out and seeing for the first time what would be happening. So it'll be just a very exciting and unique time for the end of the mission. And now what I'd like to do is just sort of show you a very short concluding movie, and then I'll take some questions. What exactly are we going to be doing in the next 3 years? There's a lot of really cool, exciting science, and I'm sure we're going to make new discoveries in that time. So for that final 3 years, here's what's in store.
Cassini is there in the Saturn system now, has been making discoveries for the last several years, and there's more to come. By studying the satellites in the Saturnian system, we begin to understand something also about the origin of the solar system.
There is strong evidence now that most of the surface of Titan is in fact covered with organic material of some kind.
We're going to be looking at lakes on the surface of this moon in detail. We're going to be looking at the atmosphere to see how the climate changes over time.
We have some global circulation models that tell us as the winds pick up, we think there could be waves on the lakes of liquid methane.
Can you imagine anybody thinking that we would discover active cryovolcanism on one of these moons? Geysers? One of the things that we'll do in the next couple of years is make the first ever flyby through the plume when the plume output is at its maximum.
And then, of course, there's the planet Saturn itself. As we go through our series of orbits and as the seasons change, it's like having a brand new mission.
One Saturn year is nearly 30 Earth years. To be there for nearly half of a Saturn year is a once-in-a-lifetime opportunity.
The sun now is coming up on the North Pole, so we're getting to see territory that was in darkness when we first arrived in 2004. Pretty soon we'll have the whole hexagon and the hurricane inside of it illuminated by the sun. And then, of course, the mission's end itself is completely unique.
Starting in 2016, ending in 2017, these orbits will take us up and over the north and south poles of the planet.
We're actually going to dive in between the innermost edge of the D-ring and the upper atmosphere of the planet itself.
From that, we're going to learn how is Saturn constructed from inside out.
We'll also get the magnetic field of the planet, the mass of the rings for the very first time, and get to sample a place that no spacecraft has ever flown before.
This is a mission that cannot be duplicated. So we really want to take advantage of this opportunity to observe seasonal variation in the system.
Now, what I like to say is with Cassini, we had a rare opportunity, and we've seized it. So thank you very much. I'd be happy to take questions. There's a mic set up in the middle. If you could go to the mic for questions, that would be great.
Yeah, fascinating presentation. Thank you very much. You mentioned something about how when there's equinox, it's like the least visible time where you can see those rings. I'm curious, from the time that they discovered, I guess was it Galileo who was looking at the rings and everything, when did they first start to discover on Earth, or somebody make note that at certain times of the year, those rings are less visible? Is it something that was just discovered recently, or did like Galileo comment on it? And at what time did you finally discover that the reason you can't see those rings as well is because of the equinox?
No, actually, Galileo inadvertently discovered it. When he discovered Saturn's rings, he thought that there were two large moons, one on either side of Saturn. And with the telescope he had, and he kept observing, and then all of a sudden he noticed that those moons disappeared. That was equinox. The moons were edged on not only to the sun, but to the Earth as well. And then then those objects, which were the rings, later reappeared. So once we figured out that was a sheet of material around them and not two moons, then we could figure out that twice every orbit, every 15 years, the sun is edged on to the rings.
Okay, at what time did you make that discovery? Is that one of the things you learned with Cassini, or did you figure it out before that?
Oh, we had figured it out long before, all the way back with Galileo. Shortly after Galileo, people figured out that you actually had rings there, not moons. As the telescopes got better and better, it was clear that they weren't moons, but rather a sheet of material completely encircling the planet. So we've known about it for a long time.
Okay.
And we've never been able until Cassini to be there, where it's edged onto the Earth, to be there with a spacecraft to look down on the rings and watch as equinox happens.
Okay, thank you.
Great. Well, I'm excited again about the next 3 years. I know there was debate about was there enough tidal pulling on Enceladus to create all that heat and make that seem reasonable that it would have that much activity. Is there any more thinking about that?
That's a good question. Does Enceladus have enough tidal energy to actually maintain a liquid ocean that supports the geysers and jets? And we didn't think so. We're still doing the math and trying to figure it out. So that is a very interesting puzzle. Basically, Enceladus is in resonance with another moon, Dione. That makes its orbit non-circular, so it feels these stresses. If you've ever squeezed a rubber ball, as it heats up, if you keep squeezing it in the same way, Enceladus is being squeezed as it orbits Saturn. But we're not sure what that answer is yet. We're still working on it.
Thank you.
So thank you very much for your presentation. 2 quick questions. First, why half a Saturn year? Why not a full Saturn year?
Good question. I'd be all for that. Good question. Yeah. So you can stay longer. Okay, go ahead. Yeah.
And what's the planned follow-up? Because obviously there's plenty to be seen in future missions, so when do we come back?
Yeah, both good questions. Yeah, we would love to go another 10 years. The problem is we're running out of fuel on Cassini. And so we figure we can make it to 2017, but the fuel will be so low at that point, we need to end the mission. So what we're going to do is on one of those final orbits, after 22 orbits in that region, that final orbit, we get a little nudge from Titan that lowers our periaps, and we actually go into Saturn, and the Cassini spacecraft basically vaporizes. And the reason we have that end of mission is because we have 2 worlds, Enceladus and Titan, that have liquid water oceans. And so for planetary protection, to make sure that we don't take our RTGs and melt through the icy crust and get into the ocean inadvertently, if we had crashed on one of those moons, we want to make sure that doesn't happen. So the safest thing to do is to put the spacecraft instead into Saturn. And hey, by the way, you're going to get some really great science while you do that.
So in mission planning, why not add about twice as much fuel and have...
Well, as you can see, it took us already 7 years to get out to Saturn because you had gravity assists, 2 of Venus, the Earth, and Jupiter. And you would have had to have even more gravity assists and a bigger fuel tank to carry enough fuel to last a little bit longer. But as far as missions to go back, there's a New Frontiers line with NASA. In that New Frontiers line is a Saturn probe. And so we might have a probe like Galileo did to probe into the atmosphere of Saturn, learn even more about its origins and its composition. I think it'd be great to have a mission to go back to, like I said, to Enceladus, to fly through the plumes with the instruments that you need to see if you might have life there, or collect a sample and bring it back to Earth. How about a Titan orbiter? Let's really map out the surface of Titan, and while you're at it with the orbiter, why not carry some kind of a balloon you could put in the atmosphere so it could float around, like the Goodyear blimp, and then take measurements. And then how about another probe or two, and one to go into a lake and one to go into a dune, So there's a lot you could do with Titan as well. And then a mission I really like is you could have a Saturn ring observer, to have a spacecraft that would use maybe ion propulsion or nuclear propulsion and hover over the rings, kind of move across and sort of be close enough to actually watch the ring particles interacting. And I think that would be a cool mission as well. So lots of potential to go back to Saturn. When? It could be a long time. It could be a long time.
Thank you.
Hello, thank you, a good presentation. In regard to Enceladus, having eccentric orbit, has it actually added to thermal convection?
The eccentricity that sort of as the resonance with Dione results in squeezing, perhaps that's going on in the interior. That's a really good question. We know the ocean is in contact with a rocky core that's inside. Enceladus is differentiated, ice on the outside, rock in the middle. And that could be contributing to some kind of convection that's maybe helping pump the material out, up through the cracks and into the geysers. So there's a lot we're still trying to figure out with those.
Thank you very much.
Sure.
First of all, thank you for the excellent presentation. I really enjoyed it. But I was wondering, with Saturn's complex moon system and ring system, how do you get the two sort of interacting gravitationally, with some of the moons affecting it and some not affecting the rings of Saturn?
That's a good question. A lot of the structure in the rings is actually determined by interactions with the tiny moons that are closest to the rings, and even Mimas has some interactions. Mimas is actually controlling the resonance with the outer edge of the B ring. So it turns out probably over time these moons shift in their orbits. They probably tend to want to move out until they get maybe locked into resonances with them. In fact, we kind of use how far away a moon might be from the edge of the ring to sort of maybe gauge the edge of the ring, because these moonlets, as they give energy to the ring, they move further away. And so we kind of try and use that as a gauge to see how old the rings might be.
Thank you.
Very quickly. Beautiful talk, by the way. I just noticed in that small video clip of the storm in the middle of the hexagon, it seemed as if there was clouds and they were moving in opposite directions to each other. Just wondering what the cause of that was.
That's a good question. In that movie, Inside the Hurricane or Inside the Hexagon, they had to basically pick a feature or something and use that as zero. And so some things move faster than that feature and go one direction, and some things move slower than that feature and go the other direction. But everything is really rotating in the same sense. In other words, if you pick the slowest rotating feature, then everything would go around the racetrack in the same way. But it's just from how they picked the 0 point.
Oh, perfect.
How you get that.
Great.
Yeah.
Looking forward to the future. Thanks.
Yeah.
Chemistry question. Do we know what's making the parts of the atmosphere blue?
Do we know what's making parts of the atmosphere blue? That's a good question. We have some ideas. When we look inside the hexagon, we can measure the sizes of the haze particles. We know the haze particles are smaller inside the hexagon, so it could be that when you don't have sunlight for a long time, the larger haze particles break apart. And it takes a while then with sunlight to regrow them. So that's one idea of how you could get those different colors. So the haze is kind of like a high-level bunch of big particles that's creating that golden color on Saturn.
Hello. My question is about the interior of Saturn, what we know about if there's a liquid surface inside of the atmosphere, and if there's a solid surface under the liquid surface, and what we know about how those are rotating in relation to each other and in relation to the storms.
Yeah, Saturn is basically made of gas, mostly hydrogen with some helium. It has no solid surface. And so what happens is that gas compresses and compresses and compresses until it gets into kind of a liquid metallic phase. And we think that metallic phase is where you generate the magnetic field. There might be a small Earth-sized rocky core at the center of Saturn, but there's really no solid surface, and then there's just this very, very hot metallic hydrogen phase. If you think about it, if Saturn were quite a bit bigger, and it could have compressed enough, it could have become a star. It could have become like our sun. It's just not big enough to actually have gone that far.
And do you know how quickly if the liquid or the compressed metallic liquid is moving differently than the atmosphere, or?
That's a good question. We thought we knew with the Saturn kilometric radiation period, we thought we knew the internal rotation rate, but now we don't. So we're hoping when we get in these very close orbits, the problem is the magnetic field and the rotation axis are almost perfectly aligned. Other planets, it's tipped like the Earth. It's tipped a little bit, and so it's very easy to see what the internal rotation rate is. Saturn, they're almost perfectly aligned. We're hoping to get really close. If it's only offset by 1/10 of a degree or a very small amount, we'll be able to sort that out. But we do want to answer that question. That's an important question.
Thank you.
Sure.
Can you talk more about the Huygens probe and what we discovered and what was the original plan? There was a reason for the probe. And did we discover what we really had been interested in the first place?
Right. The Huygens probe, the main purpose of it was to get below that haze and see what the surface of Titan looked like. And also to measure the changing composition in the atmosphere as you went all the way down to the surface. And what's interesting with the Huygens probe is initially we didn't know what the surface looked like. We knew there was a lot of methane in the atmosphere, that the methane would rain out. We were expecting an ocean of methane, perhaps a global ocean of methane on Titan. And so we built the probe to float, at least for a few minutes, in liquid methane. And so we were very surprised to find that there is methane as a liquid form, but only primarily at the North Pole. And so the goals for Huygens were to measure the composition of the atmosphere as you went down through the atmosphere, to see what the surface looked like. And we actually had a light that came on as we got close to the surface, so as we were taking pictures, we would know what the color of the surface was and what the composition was. And the bonus was that Huygens survived the landing, that we didn't know if it would survive or not. If it was in a liquid methane ocean, we figured it would sink after a few minutes or the batteries would get too cold to operate. So we landed on the surface, heated it up, and vaporized a bunch of gases that we could then measure with our instruments, and then continued to take pictures. We actually saw the shadow of the parachute go across as we were taking pictures as it came down out of view. So we accomplished the goals with Huygens and more, and it's just so many times when you explore, you answer the list of questions that you have, and then you generate a list of questions that's maybe 10 times longer that you want to go back and ask and address those questions. And we have so many more questions now about Titan.
On future missions, if probes determine if there are biological life on Titan or Enceladus, right? What would be the next steps?
Wow. That's a very profound question. If we really found that there was some kind of life there, then I think we'd be very careful not to want to contaminate in any way that life with microbes, from the Earth. I'm sure we'd want to study it further. Is it life like the life we're used to here on Earth? Is it very different? Just to sort of open up and ask those questions. Is the life we have on Earth special? Or when you have life, is it always in the same amino acids and the same compounds that form life? So it would be awesome to find that.
Thank you.
Can you describe a little bit about the spectrometer that's on board Cassini and perhaps what kind of things it could detect, its limitations, and what would be desired in the future? Is it a multispectral spectrometer? Is it a hyperspectral? Just a little bit.
Okay, the spectrometers on Cassini, we actually have several. They're in different wavelength bands. We have an ultraviolet spectrometer that's very good at detecting atoms, different kinds of atoms that way. We have a near-infrared spectrometer, and it can detect compounds by looking in the near-infrared. Then we have a far-infrared set of spectrometers as well, and they actually look at the molecular bonds and can detect compounds that are larger as well. So you have a whole, actually separate instruments. Cassini, you really, we're carrying a lot of very sophisticated instruments for its day. And so you have these separate sets of spectrometers, and then some of them overlap in wavelengths, so you can do cross-calibration. And then the cameras have, these spectral windows that they look through that contribute to it as well. So we have a lot of very sensitive spectrometers.
Thanks very much. I had some questions about Enceladus's motion. Does it rotate on an axis? If it does, is that axis perpendicular to its path of travel? And if it does rotate, can you talk a little bit about the tidal forces and why they would manifest themselves in the southern hemisphere as opposed to equatorially?
You ask a whole host of very good questions. So I'll try and touch on those, and if you want to talk more afterwards, that would be fine. The moons around Saturn are pretty much like our moon. They always keep one side facing Saturn. Their poles tend to be, with the exception of Hyperion, which rotates chaotically, but their poles tend to be pretty much perpendicular to their rotation axis as they go around. In the case of Enceladus, though, in some of these moons, there's what they call libration, which means, and our moon does this too, it doesn't quite keep one side facing. It tends to wander or librate back and forth a little bit as it orbits around. And you've asked a whole host of very good questions. Why just the South Pole? There are some models that suggest if you had an active plume that perhaps formed elsewhere, it would tend to want to go to one of the poles. We have a flyby coming up in the end of 2015 that's going to look specifically at the North Pole. The North Pole's been in darkness. We have some Voyager data in the north, but we want to look and see, are there evidence for ancient tiger stripes, ancient activity in the north? Maybe the north froze up faster. Maybe it was never active. But that's a question we really, really want to study. So there is a reason for why it would be in the south, but why one pole? That's a little harder question to answer. I'd also point out that Jupiter's moon Europa seems to have plume activity with it as well, and that they have been looking at that. And that's another world to go back and explore with a liquid ocean, too.
Doctor, fantastic presentation. Thank you. Did I hear correctly that there's a figure of 30 feet thick of the ring? And why not 60 foot then?
30 feet or less. They're really not very thick. Saturn's oblate, and its oblateness happens to want to keep those ring particles all in one plane. There are places in the rings where you're bigger than 30 feet. There are things called bending ways where the ring particles actually go above and below. We saw some structures at equinox, but in general, the rings on average are only about 30 feet. You could think of paper thin given those 100,000, almost 200,000 kilometer extent of the rings. Very thin. Okay, I guess there's just a couple more questions here. I think people have been watching on the internet. So just take a quick look at the questions. Oh, here's a tricky one. Is Titan a better target than Europa for finding life? Is it easier to get a probe in Titan? That's a very interesting question. Yeah, in the case of Titan, it could be that the ice layer is thicker than it is on Europa. In both cases, you have, looks like pretty much an ice shell, and then you'd have to go through the ice shell to get to the liquid ocean. So I think the ice crust on Titan may be a little bit thicker. Europa is interesting now. If you do have plumes, then you might be getting material out, and there's evidence of cracks and fractures that there might be the equivalent that you could go down through a crack. So now, if you ask me about Enceladus and Europa, that would be a little trickier. So let's see. Was the pendulum motion of the Huygens probe an intentional design decision? No, it's basically, it was hanging from the end of the parachute, and things tend to kind of sway back and forth, and actually the probe was rotating. It had fins on it to make it rotate, and the interesting thing about the probe is the fins were supposed to make it rotate one direction. We dropped it out of planes and all this good stuff. What happens it gets to Titan? It rotates the opposite direction. Why? We have no idea. So, but there were winds and probably gusts of wind as the probe was going down, and that probably created some of the pendulum motion. And like I say, the fins, maintained the rotation, but the wrong direction. So something interesting there. Let's see. Name one thing that would be the most satisfying to have confirmed during the next 3 years. Very interesting to have confirmed. Wow, I have a list, of things that would be nice to confirm in the next 3 years. I think a very fundamental thing, it's not as splashy as some of the pictures, but to really understand Saturn's internal rotation, I think will be a very fundamental answer to the question. And I think getting the mass of the rings and determining their age, I think is also a very interesting thing. So that end of mission, that's the place there'll be a lot of interesting new discoveries, unexpected discoveries. So, okay, so some good questions from the people out there listening in. So, okay, if there are no more questions, thank you very much for coming. Really appreciate it. Thank you.